We see some sort of oscilloscope looking device with some analog signal displayed on the screen. And these devices allow us to look at a raw analog signal, which comes in through one of these inputs, and then it graphs this signal on an axis where the x-axis is time and the vertical y-axis is voltage. So we can use the knobs on the oscilloscope to zoom in and out in the time axis and in the voltage axis to the size that we think the peaks may be for that detector and these particles. And then if we see peaks, then we know that a particle has hit the crystal, created light, and that light has been transferred into electrons, which are then amplified into a signal that we can see. So if there are no particles hitting the detector, we expect to see something like this, where we have our time on the horizontal, voltage in the vertical, and we see just this fuzzy line of nothing in the middle, just pure noise in our signal. Whereas if we do see a particle, then we see something like this, where we have our flat, noisy signal, and then at the instant that the particle was detected, we see this huge spike that goes up very quickly, and then we see this exponential decay that goes out from that due to the electronics within the detector, and then it eventually returns to ground and we see no more signal again. On whatever count rate of particles we have, or how often particles are hitting the detector, we would see peaks every time we see a particle. So if you have a very high or very fast count rate, then that would mean that you would have peaks almost all the time, sometimes even bunched on top of each other. But then that begs the question, how do we look at this peak and gather anything from that? It just looks like a spike on a graph. Well, if we see a peak that looks like this, then we can see the height of this peak here. And this is measured in volts because the vertical axis of the oscilloscope is voltage. But because of the way that the detector is built, we know that the voltage of this output signal is directly related to the energy of the particle that came into the detector and made this peak. So if we know the voltage, we can immediately figure out what the energy of that peak was. And additionally, we can look at this peak, and by measuring how long it takes the peak to go from the top back down to the original noisy signal, we can measure the time of that peak. And so now that we're talking about the energy and the time of the peak, that brings us into our conversation about the precision of these detectors and crystals, and how precise can we really get with these tools. When we're evaluating the type of crystal scintillator that we use, we look at two main parameters, and those are two different kinds of precisions that the crystal will have based on its inherent qualities. And these are energy resolution and timing resolution. If we think about resolution in the sense that we are familiar with it, you may think of looking at a picture, and the resolution of the picture would be directly related to how many pixels are in the picture and how much detail you actually have in the picture when you zoom in. And the resolution can tell you how far you can zoom in before it will start to get blurry and you'll start to notice those individual pixels. So in a similar way, when we think about energy resolution, what that really means